Good evening, all of you. Is the voice clear to all? And the video also? Is it fine for everyone? The voice and the visual? So let us start our today's session. In the previous class, we discussed about homomorphism and fundamental theorem of homomorphism and some problems based on that. So do you have any queries on the problems or theorems what we have discussed earlier? Please tell. Any questions or any doubts for anyone? With regard to fundamental theorem or the theorems before that? If you are clear, then the objective of today's session will be, so let us discuss some problems earlier first. Then we do with some of the good results based on fundamental theorem. So this will be the objective of today's session. So please take a note of it. Then I start our session. Right? So you consider the function f from g to g defined by f of x equal to x square for all x belongs to g. So if this is a homomorphism, then our claim is G is abelian. So if the mapping f from G to G itself defined by f of x equal to x square is a homomorphism, then we have to show that G is abelian. This is the problem. So take a note of that. So to prove this, as for the property of abelian is concerned, you have to show that xy is equal to yx. If you take any two elements in the group, we have to show that xy equal to yx. So for this, let us consider the two elements in the group. So from the very definition, applying to these elements, so we have f of x equal to x square and f of y is equal to y square. Yes, and when you take two elements in the group, by closure law, xy also belongs to the group. And from this definition, so whatever the element you take in the group, f of x is nothing but its square. Since xy is an element in the group, we have f of xy equal to xy whole square. Since f is a homomorphism you have taken, so from this you can write that f of xy is equal to f of x into f of y. So substituting the respective values here, xy whole square equal to x square dot y square. This is nothing but xy equal to x into x, y into y. So if you apply cancellation laws here, you can cancel the leftmost element, you can cancel the rightmost element, so which gives that yx is equal to xy. Therefore, G is abelian. So please take a note of this. Any queries you can ask. If it is clear, then I discuss the other part, the other problem. Please let me know after noting. So can I proceed further? So can I continue? Right. So another interesting problem is, you take the function f from g to g by f of x equal to x inverse. Now, the interesting concept here is f is automorphism if and only if G is abelian. So this is one interesting problem. Let us discuss on this. So first of all, take a note of this. So if f from g to g is a function defined by f of x equal to x inverse for every element in the group G, then it becomes an automorphism if and only if G is abelian. Now, you know that what is meant by automorphism? It is nothing but homomorphism and a bijection. Since it is defined from G to G itself, so isomorphism, automorphism both are equal. So isomorphism if and only if G is abelian is our criteria to prove. Is the context clear for everyone? Say. Right? So since it is if and only if condition, it has two parts to prove. So let us consider the main part. So we assume this. So our claim is G is abelian. So F is an automorphism. We have assumed this. We have to prove that G is abelian. Now let us take two elements in the group. Now you consider f of xy. As per the definition of f, this value is nothing but xy whole inverse. And from the property of calculating the inverse, this equal to y inverse x inverse. Again, using the same definition at this part, we can write it as f of y into f of x. This is nothing but f of yx. So how this is written? Since f definition, this is property. Again, you have written f definition. Since f homomorphism. So these are the reasons for my framing. Therefore, you got that f of xy is equal to f of yx. Immediately you can say that xy is equal to yx since it is a 1-1 function. You have assumed that it is a homomorphism as well as a bijection. Since it is a bijection, it is 1-1 and onto function. Hence, using 1-1 property, as and when the images are equal, elements must be equal. So this gives that G is abelian. Any questions for this part to anyone? Please take a note of this. After noting, please tell. Right? So then we discuss about the opposite part, the converse part. So now we are assuming that G is abelian. So we have to prove that F is an automorphism. So nothing but F is 1-1, F is onto, and F is homomorphism. So these things we have to prove so that F becomes automorphism. So if you consider the first one, it is very easy. So you take x and y two elements in G such that f of x equal to f of y. So which gives that x inverse equal to y inverse. Taking inverse on both sides, x inverse whole inverse equal to y inverse whole inverse, which gives that x equal to y. Therefore, f is 1-1 is proved. Any questions for anybody? How we have proved this? Yes or no? Please tell. Please take a note of that. After noting, please tell. Right. So coming for onto part, so for every element in the codomain, we have to find an element in the domain. Yes? So we have to start with this. So we are taking two elements such that f of x equal to f of y, so that you are putting x equal to y. How do we prove one function? The definition is, if elements are different, then images different. Actually, this is the definition. So how we are going to prove that? If images same, then elements same. Right? So this is the strategy to prove. So this is a strategy while proving F is 1, 1. Clear to all? Right. So for every element in codomain, we have to find an element in the domain. So here we need to understand that the function is from G to G itself. So it is a function on the same set. So if you take an element X in the codomain, the corresponding pre-image is nothing but X inverse. So if you take that X belongs to G, that is codomain, then X inverse belongs to G, which is in the domain. So if you consider f of X inverse, from definition it is X inverse whole inverse, nothing but X. Therefore, F becomes onto. Any doubts? Yes or no? Right. So coming to homomorphism, so you take two elements, consider f of xy. So this is equal to xy whole inverse from the definition of f. This is equal to y inverse x inverse. Now the interesting thing is, since we have assumed that G is abelian, so this is equal to x inverse y inverse. So at this part, we are making use of the abelian property. Till now, we didn't use the abelian property. Please understand. So while proving homomorphism, we are making use of the abelian property. And this is nothing but f of x dot f of y. Therefore, f is homomorphism. That's all. Please check on that. Any questions or any doubts for anybody? So please take a note of this. After noting, let me know. I will go for some interesting concepts after this. If you have any doubts with regard to the methodology, you can ask. Yeah. The definition of onto, if you consider, for every element in codomain, there exists pre-image in domain. So that under the function they paired. So this is the concept of onto. Do you agree? Say yes or no? Right. So please understand that here the domain, codomain both are same. This is the same set. Domain is the group G. Codomain is also the group G. You are taking a function, the set to itself. You are not taking a different set. What are the elements here are the same elements here also. Nothing changed at all. So if you take X in the codomain, since G is group, so X inverse belongs to G. So X inverse is a part here and here. Both sets it will be there because you have taken the same set. So for this, the pre-image is X inverse. So if you consider f of X inverse, from the definition, it is X inverse whole inverse, nothing but X. This is the ideology. So if you have a confusion, if you take X inverse here, the pre-image will be X here. So that these are getting related under the function. Clear now? Because you have taken the same set. You didn't take any distinct set. Is it sufficient or you need more elaboration? Fine. Because it is possible because you have taken the same set. If the set is different, you have to calculate what here. In this set, what is to be there. Fine. Now, we introduce the concept of canonical homomorphism. The definition. So, it is very simple. If you take G as a group, H is normal subgroup of G. Then you have H, G by H is the quotient group. Okay. Now, are they connected? So the concept is, if we have taken the group G and the quotient group G by H, are you able to find a homomorphism between these two? If it is existed, that we are calling it as the canonical homomorphism. So the definition is very simple. You define the function f from G to G by H by f of x is equal to hx. You can easily verify that it will become a homomorphism, because if you consider f of xy, it is nothing but hxy. So hx dot hy as per coset multiplication, nothing but f of x dot f of y. So this is a homomorphism. So this homomorphism, you are calling it as canonical homomorphism. So please understand that here you are pairing an element with a coset. One element, one set, these two put together so that you are building a homomorphism between them. And if you have a questions, what is the kernel? The kernel is nothing but H here. Because so in G, H is the part. So kernel is nothing but H, and you have taken that H is normal subgroup of G. So this is the objective. So is it clear, the definition? What is meant by canonical homomorphism? The homomorphism defined from group to the quotient group in the property that f of x is equal to hx. In this way, we are defining the homomorphism between these two. So the element is paired with the set. Element set relation it is. Okay. Any questions you can ask? So one interesting concept is, in the previous class we have proved fundamental theorem of homomorphism. Using the technique of it, we are going to prove two theorems. We call them as second isomorphism theorem and third isomorphism theorem. The strategy is based on the fundamental theorem. Once you understand how we are defining a function, then it is very easy to prove that. Okay. So if we have noted this, I will go to that context. And these two theorems are given in the previous year papers. Please understand that. These results are given in the previous year papers. Shall I proceed? Right. In the syllabus, you can look into the concept that isomorphism theorems. It was given in the syllabus that isomorphism theorems. So actually we call them as second isomorphism theorem. The statement is given by this is the statement of second isomorphism theorem. Please take a note of this, then I will discuss with the approach. Once you noted, please tell. Right. So, if you talk of fundamental theorem, in this we prove that G by kernel is isomorphic to G dash, where F is a homomorphism and onto. This is the concept of fundamental theorem. So what it says, whenever you have two groups, G and G dash, your duty is you have to define a function f between G and G dash as per your convenience. And you have to show that the function f, what you defined, must be a homomorphism and onto. Then the theorem states that domain by kernel isomorphic to codomain. The concept is domain by kernel is isomorphic to codomain. Is it clear? Yes or no? So the same strategy I am going to follow here. So my strategy here is I want to build a function from k to hk by h. So, and I am going to prove that that function is homomorphism and onto. This is my claim. If I can build a function from k to hk by h, which is homomorphism and onto, then as per the fundamental theorem, k by kernel isomorphic to hk by h. So kernel here equals to h intersection k. So this is the whole idea in proving this result. Are you clear? Say what I am actually going to do for proving this result. And first of all, tell me, did you understand the concept of fundamental theorem of homomorphism? Yeah. Did you understand this concept? Everyone, please tell. Right. So here, this is our claim. We have to prove that hk by h isomorphic to k by this. So you first forget this one. Now, I have two groups. One is k, one is hk by h. So if I build a function from k to hk by h, which is a homomorphism and onto, then I can make use of this statement. So from this, domain by kernel isomorphic to codomain. So domain by kernel isomorphic to this. So, and what will be the kernel? And I am going to prove that kernel is nothing but h intersection k. In that way, the claim completes. Clear now? Yes or no? All of you. Right. Now, let us go for the part. So I will erase the total things so that representation makes you good understanding. So I am going to define a function between them. So I want to define the function from k to hk by h. How? So how to define the function here? The question is, this is a group containing only elements. This is quotient group contains only cosets. So if you want to pair them up, you have to pair an element to a coset here. So we define that f of x is equal to hx. This is my definition. Okay, how it is defined? Left side contains elements, right side contains cosets. Is it clear? Yes or no? Right. Now, is it well defined? So well defined in the sense, whenever elements are equal, corresponding images are also equal. That type of situation we call it as well defined. So if you take that x is equal to y, then you have f of x is equal to f of y, which gives that hx equal to hy. So it is well defined. There is no need to check that separately. So whenever elements are equal, images are also equal. That type of notation is called as well defined. And here the function how I have defined is by default an onto function. There is no need to check that separately. So assume that it is onto right now. If you have a doubt, you can cross verify that. But the very definition, it is an onto function. Now the question is it a homomorphism or not? So if you check for homomorphism, consider f of xy. This is hxy, nothing but hx dot hy. So equal to f of x into f of y. Therefore, it is a homomorphism. So we have defined a function which is a homomorphism function and it is onto also. So here I am not proving onto. The very function is onto. It is in the form of canonical homomorphism. So it is always onto. Yes, that's what I am saying. If you are interested, you can do, because it is of the form canonical homomorphism. So there is no need to prove that separately. So if you are interested, you can prove that, right? Okay. That's why I am skipping that part. There is no need to show that separately. It is onto by default. Therefore, by fundamental theorem, you can have that K by kernel F is isomorphic to HK by H. So here our intention is, what is the value of kernel F? We have to calculate what is the value of kernel F. So that we are going to discuss now. So if you write kernel F, set of all elements in the domain such that f of x is equal to identity in codomain. This is the definition of kernel F here. So this is set of all x belongs to K such that in this codomain, what is the identity coset there? Identity coset, because codomain is nothing but set of all sets. So what is the coset there? H. So f of x is equal to h. So here this is set of all x belongs to K such that as per f of x definition, hx is equal to h. Again, we have one good famous result in cosets. This is nothing but x belongs to k such that x belongs to h. Since we have result that x belongs to h if and only if hx is equal to h is equal to xh. Could you recollect this result? In cosets we have discussed about this term. How to prove this? We have discussed that. So as per that part, since hx is equal to h, from this you can write x belongs to h. So at this part what we got? X is belonging to h and x is belonging to k. So this element is common for both the sets, k as well as h. Therefore, this is nothing but h intersection k. Therefore, kernel F is nothing but h intersection k. So please take a note of this. Any doubts for anybody? How we have applied the fundamental theorem here? Any questions or any doubts for anybody? Say, yeah. So in this definition, where you have doubt, please tell me. Right from the beginning. From the beginning you have doubt? Yeah. So is this part clear for you? This part? Clear or not? So did you understand this part? Is this you understood or not? Is everyone getting no video? Say, how many of you have trouble with the video right now? Tell me. What about the others? Are you comfortable with the video or you have any issues? Let me know. Fine. Then, however, you try to imagine that, as per my words, if the video is not clear for you, so the kernel is nothing but, suppose I have written the sets as, say, this is the group G, this is the group G dash. So I have taken in the group as E1, 2, 3, 4. These are the elements. And in the codomain, I have taken the elements as E dash, A, B, C, D, E, or F, let us say. Now I am pairing them under my consideration. Always identity is paired with identity. So I have paired with this 3 also with identity. I have paired 1 with B and 4 with F. So if I want to know what is kernel there, kernel is nothing but the set E, 2, 3. Because E, 2, 3 are elements in the domain for which the image is identity. So in the domain, you are selecting the elements for which the image is identity. That is the concept of kernel. So here also, if you talk about the kernel, you are going to check the elements in K for which the image is identity in the codomain. So I am taking or I am selecting in the whole set K what are the elements X are present such that the image for X must be identity in the codomain. And here, what is identity element in the codomain? It is the set H. So I am checking for the elements X belongs to K such that f of X is equal to H. So as per F definition, f of X is nothing but Hx. So Hx is equal to H I got. And again, as per quotient properties, X belongs to H, as and when Hx is equal to H. Now here, X has two properties. X is an element in K and also it is an element in H. So X is belonging to the two sets, H as well as K here. So this is nothing but H intersection K because X is the common part for H as well as K. Therefore, kernel is nothing but H intersection K. Thus the theorem is proved. Okay, right? Clear for everyone? Right? Then similar kind of theorem is there that we call it as third isomorphism theorem. This is also having the same pattern that we discussed now. Then we can say isomorphism theorems are completed. Now we discuss about the third isomorphism theorem. Now we discuss about this. So coming to this part, the statement is if H and K are two normal subgroups of G, such that H subset of K, then G by H isomorphic to K by H. This is third isomorphism theorem. Please take a note of that. Understand that all these theorems are given as UPSC previous year questions around the year 2000 and odd. Okay. So if you are lucky, you can have the same theorems again to prove. Because for theorems, you will be given full marks. You will be awarded with full marks. Because you are not going to do, you are simply presenting the proof as it is. That's all. So understand the criteria that for a group G, I have taken two normal subgroups. So you can imagine like this. This is the group G in which K is the big one and H is the small one. So K and H both are normal subgroups of the group G. Then you have to show that G by K isomorphic to G by H by K by H. That's the thing you need to prove. Okay? Is the statement clear? All we are going to do is nothing but whenever you have two groups, you are simply constructing an isomorphism between them. All we need to do is we have to find a function which satisfies the criteria of fundamental theorem of homomorphism. That is actually we are doing here. So here also we follow the same strategy. So again, to prove that these are isomorphic, my intention is nothing but I am going to write a function from g by h to g by k. I have to define a function such that I am proving this function is a homomorphism and say onto. Hence, by fundamental theorem of homomorphism, g by h by kernel is isomorphic to g by k. And at the end, I prove that kernel is equal to k by h. This is the whole strategy. If you understand the previous theorem concept, the same concept we are going to apply here. All I need to do is, I want to build a function from g by h to g by k, and I want to show that it is homomorphism and onto. By default, it is an onto function. There is no need to show that separately. And by fundamental theorem, that is satisfied. And at the end, we are going to prove that kernel value is nothing but k by h. Hence, by substituting kernel value, you will get the required equation. Please check. If you have queries, you can ask. Are you clear? Yes or no? Are you clear? The approach. Right. So in the first phase, I am going to define the function f from g by h to g by k by, now understand, this is a quotient group. It is also a quotient group. In the quotient group, how would be the elements pattern? So if you talk of in general words, in g by h, every element will be of the form hx, hy, etc., etc. So nothing but h multiples. In g by k, every element is of the form kx, ky, kz, etc., etc. So it is of the form k multiples. So while defining the function, we define that f of hx is equal to kx for all hx belongs to g by h. In this way, we define the function. So first of all, understand the concept, how we are defining the function. Any questions? How it is defined? Tell me. Is it clear or not? Right? Then, this is a well-defined function. However, if you have doubt, you can say if hx is equal to hy, implies you can say xy inverse belongs to h, because you have the property that HA is equal to HB if and only if AB inverse belongs to H. Using this property, you can write XY inverse belongs to H. Implies that XY inverse belongs to K, as you have H is subset of K. Again, using the same result, you can say that kx is equal to ky. Same result. So which gives that f of hx is equal to f of hy. So this function is well defined. If you have a doubt, is it a well defined function or not, that you can consider. And it is an onto function also. There is no need to prove that onto separately, but if you have a doubt, you can prove onto as so this is the pattern G by K, this is the pattern G by H. So if you say, let us take, I have taken Ka here, what will be the element? So by default, it is an onto function because as and when you take the element Ka, it is a coset. Every coset is formed by means of taking elements in the group. So in the coset Ka, A is the element in the group. What is the group here? G. So for every group, corresponding coset will be there because H and K here, two normal subgroups we have taken. So for every element, you have a coset with respect to H, you have a coset with respect to K. Therefore, it is an onto function clearly. However, if you have a doubt, you can imagine this diagram. Okay? Any confusion for anybody? Is it onto or not? How it became? So take a note of this onto property. It is always onto. There is no need to prove that. If you are interested, you can prove. So shall I continue? Right. So now I am going to prove that it is a homomorphism that I want to show now. So you take two cosets hx and hy in G by H. Consider the product. Consider f of hx dot hy. Please understand, how do we prove homomorphism? Whenever you take two elements AB, you have to show that f of AB is equal to f of A dot f of B. The similar pattern I am following here. So as per coset multiplication, this is f of hxy. And as per f definition, you can write it as kxy. Again, using coset multiplication, you can write it as kx dot ky. And this is nothing but f of hx dot f of hy. Therefore, f is a homomorphism. So please check on the approach. Any questions you can ask. If you are clear, then I go to the next level. Done. Therefore, I have defined a function between the groups G by H and G by K satisfying the properties of fundamental theorem of homomorphism. Therefore, by fundamental theorem, we can say that G by H by kernel is isomorphic to G by K. So, in this kernel, I have to calculate what is the value of kernel. Hence, I am going to show that kernel F value is nothing but K by H. This I need to show. Then I am done. So, let us calculate what is kernel here. So, if you write kernel F definition, this is equal to set of all elements in the domain. So, set of all Hx belongs to G by H such that F of Hx is equal to identity in G by K. This is equal to set of Hx belongs to G by H such that F of Hx means Kx, identity is K. This is the part we have. Therefore, we can say that Hx is belonging to G by H. Since x belongs to K, so Hx belongs to K by H. Therefore, Hx belongs to G by H, also K by H. Hence, it is K by H. As K by H subset of G by H, so G by H intersection K by H is nothing but K by H. I will make space here. Because we have said that Hx belongs to G by H, Hx belongs to K by H. So, kernel is nothing but having like this. Clear? Please check with the approach. I simply used the definition of kernel only. How we define a kernel? Set of all elements in the domain whose image is identity in the codomain. Here the codomain is G by K. The identity in G by K is nothing but K. So f of Hx is equal to K. That is the way kernel defined. From definition of f of Hx is nothing but Kx. So Kx is equal to K. As per coset properties, whenever coset and subgroup both are equal, the elements belong to the subgroup. So X belongs to K. So at this part, if you have a doubt, you can write that Kx is equal to K is equal to Xk if and only if X belongs to K. This is the property of cosets we have learned earlier. So from this step you have taken like this. Since X is an element in K, so Hx is element in K by H. Therefore, Hx is commonly belonging to both the sets G by H as well as K by H. Nothing but, kernel is nothing but intersection of these two. Since As you know that this is subset of this, K by H is subset of G by H. So intersection is nothing but the small part, so K by H. Okay? Clear? Yes or no? So this is something complicated to understand, the third isomorphism theorem, especially the kernel part. So unless you are fundamentally good, what is kernel actually, in writing the definition of kernel, you cannot understand that. But this is the proof, so please take a note of this. So at this point, I want to conclude our today's discussion. So in the next class, we will meet, because we have discussed a lot of results today, so which gives a boredom for you. So these things you are asking, right? How this came? Yes or no? These things you are asking. I will tell. So this is nothing but A intersection B. Accepted? Yeah. So you can understand that here Hx belongs to G by H, Hx belongs to K by H. So Hx is belonging to both the sets. So hence belong to the intersection. Accepted? The coset is a part of this. Now see, as you have a diagram here, the largest set is G, next one is K, next one is H. So if you have a pattern like this, divide both sets with H. So what happens? If A is subset of B, then A intersection B is nothing but A. Accepted? If A is subset of B, that's why since this is subset of this, if you consider intersection, this comes, this part will come. Did you get the logic now? How it came? That's it. So kernel is nothing but K by H here. The kernel value is K by H here. That's it. So anybody has any more queries? Say. Is everyone clear with the proof of this theorem? So thank you. Then let us meet in the next class. Thanks for your cooperation.